Hi everyone. We're looking at lesson 7 today, combinations of functions. We're going to perform some operations on functions, do composite functions. Let's get started. We can combine two functions to create new functions. As long as the two functions have overlapping domains, and we can add, subtract, multiply, and divide functions to create totally new functions from those operations. It's important to note that in each case, the domain of the new function has to have all the numbers that belong to both the domain of f and the domain of g. And we can't have any zeros in the denominator when we're having a quotient of two functions. So let's explore a little bit algebraically. Let's say we had f of x and g of x and we wanted to subtract the two. So that's just as simple as saying 5x minus 8 and 7 minus 2x squared. We're going to find the difference between the two. So if you distribute the operation of subtraction, we end up with negative 7 and positive 2x squared. And then writing that new function in standard form or descending powers of x, we would have this brand new function. So 5x minus 8 is a line, and we combined it with the parabola and ended up with another parabola. If you wanted to evaluate, you could evaluate in two different ways. You could either take the difference of the two functions, which is right here, and substitute 4, or you could find the f of 4 and the g of 4 separately and then subtract the two values. I'm going to choose to just substitute into the new equation we found and substitute my 4 in here for the 2x squared and my 4 in here for the 5x, and then subtract 15. So 16 times 2 is 32, and 5 times 4 is 20, and that gives me 52, and 52 minus 15 is 37. So the difference between the two is 37. That's pretty straightforward. Here we're going to algebraically define two new functions. This is pretty simple. You notice the domain on x cubed is all reals, but the domain on g only allows positive values or non-negative numbers under the square root. So we could have 0 under here, but no negative values. That means that we are going to think about x plus 1 has to be greater than or equal to 0. So x has to be greater than or equal to negative 1. And overlapping domains, this is all reals. This is only things for negative 1. So the overlapping domain for all reals, and then any values greater than or equal to negative 1, they overlap here. So that kind of helps you understand that terminology of overlapping domains. So we've got that to consider in each operation. So if I'm adding two functions, I'm adding x cubed plus the square root of x plus 1, and that overlapping domain is going to go from negative 1 to infinity. The same with the difference between the two. The difference between the two can't be simplified, but same overlapping domain. The product, not much different, just x cubed times the square root of x plus 1. Same situation, overlapping domains. But here's our problem. If we divide f of x by g of x, now I've got a different problem. I can't have a 0 down here, so we cannot include negative 1, and the overlapping domain looks a little bit different. We've got to exclude the value negative 1. I know if you've got a textbook, you might have seen a drawing or figure similar to this, talking about compositions, where we're going to actually make a new function by plugging a function into the x value of a different function. I want to make a little note about this. The g of x has to be in the domain of f of x. That means we need to restrict the outputs of g. Let's take a note on that. We want to restrict the outputs of the function g so that they are in the domain of f. So that they are in the domain of f. And I believe we'll see some situations for that in our examples. So example 3, we've got a parabola, we've got a rational function and a square root function, and we want to find the composition of f of g of x. So we read this f of g of x, and that little composition circle, that does not mean to multiply. That's a composition, that means to compose. Or we could write it this way, the f of g of x, which is telling me take the f function. So our f function is x squared plus 2x minus 1. So I want to write x squared plus 2x minus 1. And in place of that variable x, this is what's going in place of that variable x, which is our g of x, 1 over x minus 2. 1 over x minus 2. So if you wanted to simplify a little bit more, it's not really necessary, but you could rewrite this as 1 over the quantity x minus 2 squared, since 1 squared is 1. And then you could move the 2 to the numerator and subtract 1. Okay? So how's the domain look on that? We can't have 2 in the denominator. So we had to restrict the output of g so that it's in the domain of f. And the output of g, we can't have any values for 2 because 2 would make that undefined, causing division by 0. So our domain is going to go from negative infinity to 2. We'll have to skip over 2 and continue on to infinity. Now you could stop and check this with your calculator if you'd like, or save that for later on. Let's look at example B. We're going to go the other way. So we want the g, this is the g of f of x. So we want the g function, which was 1 divided by x minus 2. And in place of the x, where the x was, we're going to take the x out and substitute f of x in its place, right? So f of x was the parabola x squared plus 2x minus 1. See if I can move this way. Oh, for some reason that's going to clone everything. Let's delete that. Okay, delete that. There we go. So the domain, again, let's see. If you clean up this bottom, I believe that'll factor. So we'd have x squared plus 2x minus 3. And if you think about factoring the denominator, factors of -3 that add up to +2 would be x plus 3 times x minus 1. And here's where we need to restrict this. So we can't have division by 0 in our final function. So we got negative infinity to -3. -3 to +1, and +1 to infinity. Out of space here. And +1 to infinity. Okay, so here's our composition, g of f of x, and our domain has two values that aren't allowed. On example C, the f of h of x means the f of h of x, and f is our outside function, so that would be x squared plus 2x minus 1. And our inside function, h, is the square root of 3x. So that's going to take our place or substitute for the x value. And if you square a square root, you're going to end up with 3x squared, and 2 times the square root of 3x minus 1 gives us our composition. Now we have to think about the function. So the h of x is a square root, and the square root of 3x has to be greater than or equal to 0. So x would have to be greater than or equal to 0. No negatives. That's going to affect our domain in the composition. So only values inclusive from 0 to infinity, or non-negative values. Our last example, h of f of x, h of f of x. H of x is the square root of 3x, and we're substituting the parabola in there, so x squared plus 2x minus 1. Now, my domain in here can't be 0, and we have to figure out for the argument. I'm going to just leave the square root alone here because this does not factor. So if you wanted, you could complete the square and move that -1 out here. So let's think about this. If you complete the square, half of 2 is 1, 1 squared is 1, so I want to add 1 in here and subtract 1 out here. And if we set that equal to 0, you have a binomial of x plus 1 squared minus 2, and we can solve that for 0. So x plus 1 quantity squared is equal to 2. When we take the square root of both sides, you've also got to consider plus and minus. So x plus 1 is equal to plus or minus the square root of 2. And subtracting 1, plus or minus the square root of 2. So this is going to help us figure out what the domain is. Now, we know that the square root of, or 3 square roots of x is going to look like that. So we're already limited with only values from 0 to the right. And then when we substitute this value and get a different shape square root function, we want the value from here that's going to be positive, because that's going to move the graph some way, right? So it can't be, we know the square root of 2 is about 1.4. It's about 1.412. So if we had -1 minus, it can't be that one. So it's got to be the other root, -1, plus the square root of 2. So that would give us about 0.41. And then on to infinity. So without dragging out a calculator and looking at the graph, you should be able to reason through why that value has to be a positive value, because if you did expand this, your composition would look like 3x squared plus 6x minus 3. And it's going to have a starting point somewhere about 0.41 and go off to the right. Okay, so a little calculus analyzing going on there. Another skill that we need when we move on to calculus is to be able to look at a function and say, oh, I could tear that function apart. I've got an inside function that's x plus 3, and it got substituted into an outside function that was x squared. Personally, I see the outside function first, like this is 1 over something, and then I substituted, in place of that x, I substituted x minus 5. Same thing here. I see the square root of x as the outside function, and I substituted a linear function x plus 2. This one's a little trickier, but do you see the x squared minus 4x plus 5? X squared minus 4x plus 5 is my outside function, and then we substituted x minus 2. So here's one for you to try. If you have h of x is the square root of 3x squared plus 1, can you write h as a composition of functions in 2 different ways? So what I'm asking you to do is, how can you see an outside function and then you substituted another function on the inside? So one way is to see that the outside function is the square root of x, and the inside function is 3x squared plus 1. Can you see another way? What if you had 3x plus 1 under a radical, and you substituted x squared into that function? So 2 different ways you can look at that. In example 6, we're going to look at analyzing by using graphs. So if you have an f plus g of 3, you want to use the function f and find the f of 3, and then use the function g and find the g of 3, and add those 2 y values together. So on the f graph, the f of 3 is 2, and on the g graph, the g of 3 is 1, so 2 plus 1 is 3. On this one, we're going to find the y value on f and the y value on g when x is 1 and multiply them together. So what do you get? The f of 1 looks like 2, and the g of 1 looks like 3. So 2 times 3 is going to give us 6. On the next slide, maybe we want to view them dual page together here. Excuse me. So the f of 0 divided by the g of 0. The f of 0 is 4, and the g of 0 is also 4. So the f of divided by the g of 0 would be 1. The g of negative 1 is, what's that, 5? And the f of negative 1 is 6, and we want the difference, so negative 1 in this case. Now here we got a composition, so that we want to know the f of g of 4. So what do we have? The g of 4 is 0. The g of 4 is 0. And the f of 0 is 4. And then this last one, the g of f of 2. So on the f graph, the f of 2 is 0. And the g of 0 is 4. They were both 4. Okay, you got that? Moving on. Over on example 7, we have a table of values for f, g, and h, and we want to do some operations on those excuse me, on those functions based on the table. So we need the f of 1. The f of 1 is 4, and 2 times 4 gives me 8. And we need the h of 0. So the h of 0 is 3. 3 times 3 is 9. 8 plus 9, 17. So I can find operations and combinations using tables. In example B, the g of -2, here's -2. On the g function, we have -1. And then I need the h of -1. So when x is -1, on h, we have 1.5. So you can write that as a decimal or a fraction, whichever works for you. And then the f of g of 2, when x is 2, the y value on g is -3. And the f, no, the f of -3, so when x is -3, the f of -3 is -4. So we have 1.5 times -4. So that looks like -6. And then on C, we need to look at the table. So 2f of 3, 2 times the f of 3. So going back to the table, when x is 3, the f of 3 is 8. So 2 times 8, that gives us 16. And the h of -2, so looking at the h of -2, so when x is -2, h is 1/2. So 16 divided by 1/2 would be, keep change flip, would be 32. Now here's a little challenging one. If k of x is 3x minus 4 absolute value, for what values of x is k of x equal to the f of g of 0? So we need to figure out what the f of g of 0 is, because we want 3x minus 4 to be equal to the f of g of 0. Did we find that earlier? The f of g of 0. I don't believe so. So the g of 0 is 1, and the f of 1, when x is 1, the f of 1 is 4. So the f of 1 is 4. And then it's just a matter of solving an absolute value equation. And we would drop the bars and solve two equations. Either 3x minus 4 is 4, or 3x minus 4 is the opposite of 4. So in this case, the x value would be 8/3, or in the second case, the x value would be 0. So there would be two instances when the absolute value would be equal to the f of g of 0. Either 8/3 would satisfy that equation, or 0 would satisfy that equation. Okay, you have two application problems and we'll be finished. So the volume V in cubic meters of a weather balloon is given by 4/3 pi r cubed. If the radius is increasing at a rate of 1/2 t cubed for positive time, we want to find the volume as a function of time. So the volume as a function of the radius is 4/3 pi r cubed, and we want to take the r out and put the function of time, which would be the composition. So we're going to take out all of the r's and replace the r's with 1/2 t cubed. So volume with respect to time is 4/3 pi r cubed, and in place of r, we're putting 1/2 t cubed. So simplifying that, volume with respect to time would be 4 pi over 3, and this would be t to the 9th divided by 8. So t to the 9th divided by 8, clean that up. 4 divides 8 2 times. So volume with respect to time would be pi over 6 t to the 9th. Right? And then the last one, the number n of bacteria in a container of leftover food stored in a refrigerator where capital T is the temperature of the food can be modeled by this function. When the container is removed from the refrigerator, the temperature is 5T plus 3 on 0 to 3, where T is the time in hours. Can you find the composite function and explain the meaning and context? Okay, let's see. So the composite function would be capital N of capital T of baby T, and that would be 60 capital T squared minus 140 capital T plus 76, and we're taking out the capital T and substituting that value 5T plus 3. And then I took my calculator and found 60 times 25 times all of this turned out to be 1,500 T squared plus 1,100 T plus 196. Okay, so what does that mean in context? That would tell us the number of bacteria present after T hours of removing a container from the refrigerator. Now, just to save time, I'm not going to write that because we're going to do it again. So we want to find what's the number of bacteria present after 2 hours. So substituting into our composition, 2 squared and 1,100 times 2 plus 196. Again, I pre-calculated this. And then we can say in context. So this means that there are 8,396 bacteria present in the food. In the container. Has been out after 2 hours. Okay, that brings us to an end of this lesson. We have 2 more and we'll be done with Unit 1. See you next time.